Let's now take a look at giant molecular lattice structure. Giant molecular lattice structure differs from simple covalent molecules as the atoms are held together by covalent bonds and it pervades throughout the entire structure. So one of the examples that we have is for graphite. In the case of graphite, strong covalent bonds exist within hexagonal layers of the carbon atoms. So there's one on top and one below. And between these hexagonal layers, they are actually held by instantaneous dipole-induced dipole attraction forces. The reason is because every single carbon atom in the hexagonal layers is bonded to 3 others. So each carbon delocalizes the 4th valence electrons to essentially form a giant pi bond within the hexagonal layers. And these pi electrons are free to move around. The pi electrons within the hexagonal layers can freely move around, which explains why the graphite is a good electrical conductor. Let's take a look at the diamond. Unlike graphite, in diamond, every single carbon atom is bonded to 4 others carbon atoms. So with respect to the shape, it's tetrahedral and there's no pi electron. Hence, graphite does not conduct electricity, and strong covalent bonds help all the carbon atoms together, giving rise to its high melting point. Similarly, silicon has exactly the same structure, and silicon carbide as well. In silicon carbide, every silicon atom is bonded to 4 other carbon atoms. So if to compare the melting point of diamond, silicon, and silicon carbide, the highest will be diamond, followed by silicon carbide, and silicon will be the lowest. The reason is based on the bond energy, since the atomic radius of carbon is smaller than silicon. So hence the bond energy of C to C will be the strongest, since the bond length of C to C is the shortest. While in silicon, the bond length of Si to Si is the longest, since silicon has a larger atomic radius, so hence its bond energy is the lowest. Finally, if you look at silicon dioxide, you will find that in the structure of silicon dioxide, every silicon atom is bonded to 4 other oxygen atoms, while every oxygen atom is bonded to 2 other silicon atoms. Finally, we conclude the topic on chemical bonding. In chemical bonding, we started the topic by looking at giant ionic lattice structure, moving on to looking at giant metallic lattice structure, and then we end off today by looking at giant molecular lattice structure. For simple covalent molecules, we have studied polar and non-polar covalent molecules, and specifically for polar covalent molecules, we single out molecules which are able to form intermolecular hydrogen bond relative to those that does not.